All right, well, let's get started then. So it's great to be here today. Sorry for the technical blips. Like I said, numerical relativists, I think it's a curse of numerical relativity that we try to make computers do too much for us, and they seek their revenge by not working properly when we try to give talks on what we've done with them. Next slide. Next slide, please. Scott, you're sharing. Could you advance to the next slide? I still see the first slide. Anyone else still see it?
Yeah. I see a cursor moving, so he's probably trying to find where to move the slide.
Sure. Okay.
Or is it yours?
Yeah, just give us a moment.
Okay.
All right, great. Yeah, so BlackHoles at Home, it's a new numerical relativity code aiming to provide next generation efficiency and accuracy. Now, you may recall in previous days, during some of the tutorials, for example, people asking, well, can I just get Einstein Toolkit running on my desktop or laptop? Well, in fact, no numerical relativity code out there has been designed for the desktop or laptop. Really, numerical relativity codes have been almost entirely focused on running big simulations on supercomputers. BlackHoles at Home is unique in that it attempts to fit numerical relativity in full 3 dimensions in space plus 1 dimension in time on the consumer grade desktop or laptop computer. And with that capability, we want to launch generate the largest and most accurate gravitational wave catalog out there for binary black hole, the binary black hole problem. Why would we want to generate such a big catalog? Next slide. Because if you look at the census of detected gravitational waves to date, a large majority of them are from binary black holes. Next slide. And when it comes to extracting science from these gravitational waveforms, we have to compare each observation against millions of theoretical predictions, which themselves must be grounded in these numerical relativity generated binary black hole catalogs. Next. Next, there we go. Existing catalogs aren't large or accurate enough for planned gravitational wave detectors. That's the real problem that faces numerical relativity today. And it's a very scary thing, but that's one thing that BlackHoles at Home aims to address directly. With it, I'm developing new techniques that both reduce computational expense, fitting the binary black hole problem on a consumer grade device, and also improve efficiency. So next slide. So really, this is a doubly difficult problem that we're trying to solve. And when it comes to numerical relativity, I think this quote really rings true. Next slide. Going back to John F. Kennedy in his moon launch announcement, is establishing the Apollo program. We choose to do these things not because they're easy, but because they are hard. And of course, because they have a very important practical benefit to science. Next slide. So one need not look any farther than Eric Schneider's pioneering work in getting Cartesian AMR working in an open source context within the Einstein Toolkit. His carpet driver has been used by countless numerical relativity groups over the years to generate countless papers on important science that numerical relativity needs to cover. This is just, of course, one example of many. I mean, open up the numerical relativity literature and you'll find dozens of outstanding examples of really hard problems that numerical relativists have managed to solve, making these simulations feasible, runnable on the latest generation of supercomputers. Next slide. So AMR is wonderful, and it has been wonderful. We've heard a bit about the next generation of AMR that's going to be more scalable, make it possible to evolve Einstein's equations and coupled to the GRMHD equations with neutrino physics on the latest supercomputers, which generally are mostly GPU compute machines. But let me just say that there's another way, and that is to migrate to more efficient numerical grids. And unlike Cartesian AMR, which I believe universally throughout numerical relativity has this property where if you move away from the strong field region, around the region where the black holes lie, out to the outer boundary of the simulation, you'll notice that there's this discontinuous jump in decrease in resolution as you move out. This is very weird if you know how the space-time fields actually look in these simulations. They don't discontinuously jump, increase in length scale as you move out from the strong field region. So a more efficient grid structure would employ smoother transitions in resolution. Also, there are some near symmetries in these space-time fields that if we exploited them, as opposed to just putting down Cartesian grids, they don't look very box-like, these space-time fields. Then we might be able to get a great improvement in the efficiency in our overall numerical relativity code. Next slide. And next slide. And this is the sort of grid structure that I am proposing. So Black Holes at Home is built upon the NURPI plus code generation infrastructure that is capable of generating Einstein's equations in Cartesian-like, spherical-like, cylindrical-like, spheroidal-like, you name it, coordinates. And with that capability, we have been able to now generate this multi-patch infrastructure for solving problems in numerical relativity, like the binary black hole problem. And let me say that I've managed to accomplish a great deal in terms of efficiency. We now are capable of solving the binary black hole problem in about 3 GB of RAM, or your money back, which comfortably fits on most modern day desktops, laptops. Heck, it even fits on my cell phone if I don't like my cell phone very much and am angry at it. It's also very efficient in terms of overall CPU time. It's somewhere between a factor of 6 and 50 times more efficient in terms of total number of CPU hours needed to complete a binary black hole simulation. This is compared to Carpet within the Einstein Toolkit. And let me also say that the factor of 6 there, that is due to a core inefficiency in Black Holes at Home. And with any luck, in the next year or so, I'll be able to just report that Black Holes at Home is a factor of 50 or so faster or more efficient in overall CPU time requirements to do binary black hole as compared to traditional Cartesian moving box AMR approach. There we go. Okay. All right, so next slide. Right, so last year when I hosted the Einstein Toolkit workshop at the University of Idaho, I gave an update on the project, underscoring that it had been completely rewritten to handle mergers. And this, the key innovation here was what I refer to as a Lego building blocks approach for setting up these diverse multi-patch coordinates systems or numerical grids. And it sort of boils down to this. I wish I had a pointer. That's okay. So you can imagine, say, a Cartesian box inside a Cartesian box. You can see some examples of that on, oh, thank you, on pictured here, like especially in the merger grids, the close separation grids, you see this Cartesian box inside Cartesian box approach. That's one algorithm that I coded up, okay? That turned out to be the easiest one of all of them. You also see Cartesian box inside spherical box. There you go, perfect, that's right. And that one was a bit harder, but I managed it, and that's another algorithm. You also see spherical inside spherical, which is in the close separation. You see sort of the darker blue and the lighter green, or I guess darker blue and lighter green. That's in close separation. The middle one. Anyway, yeah, close separation grid. Yeah, so there you see a spherical inside a spherical. The outer green one is actually spherical as well. That's another algorithm that I coded up. You also see rounded Cartesian inside spherical. That's the in-spiral grids. Those small little circles there that look like the Band-Aids that you put on yourself if you get hit by, I guess, stuck by a fishing hook when you're out fishing. Also, rounded box, inside rounded Cartesian box AMR, that's also close, the in-spiral grids right there. And then you see the hardest grid structure, the algorithm to code up was sphere on top, small sphere on top, small sphere on bottom, and then large sphere outside. That's also in-spiral grids. That's a 3-grid interface. That required months of work to figure out how to do for the first time. I didn't get my PhD in grid structures, unfortunately, but I think I've managed, if there was an honorary degree in that, I probably would have earned it at this point. Move on, next slide. There we go. And I demonstrated last year nice convergence in the numerical errors, as well as a beautiful gravitational waveforms that have come out of this. And let me challenge anyone who does numerical relativity, who does binary black hole evolutions, look at your L equals M equals 8 mode. Look at the amplitude versus time like I have there on the bottom right. If you can get as smooth a waveform as this, please, please let me know. I want to know your secrets because this is very difficult to do. I've tried to do this in Cartesian AMR grids, also with cube spheres, and the noise completely drowns out the signal in this. And let me say that L equals M equals 8 is also very, very, very important for next generation gravitational wave detectors. If we see a highly asymmetrical binary, in other words, a binary black hole with a large mass ratio, this high order mode can be very, very important, but it's obscured due to numerical noise in most numerical relativity simulations. Next slide, please. So lots happened since 2022, last year. And as of April of this year, I launched the first Black Holes at Home catalog, consisting of 115 SXS catalog reproductions. This is a mass ratio of 6 or below, spins less than 0.5, and I chose the shortest cases because I'm debugging the code, working through any issues that might still exist in Black Holes at Home. And really, over this past year, Black Holes at Home has gone from sort of being in a beta phase to a much more mature code base. And I found, after looking at the latest results, great agreement in many waveforms as compared to waveforms in the SXS catalog. And you'll see there a little benchmark, less than 1 month runtime, we go out past time of 4,000 M. On the upper right plot there, you see this is the in-spiral trajectory of those 115 binary black holes on their initial orbital plane. And on the bottom right plot, you see that a lot of these cases are precessing, and some very strongly precessing. Just a reflection that Black Holes at Home supports precession. It's part of its infrastructure. All right, next slide. But there's a big problem. About 20% of the cases, we'll see what happens. I'm working to fix this problem right now. Next slide. So the problem is not in the strong field region. Here I'm just plotting 23 out of 115 binary black hole evolutions. This is like the log base 10 of the average Hamiltonian constraint violation per grid point. This is a proxy for numerical error. And you can see it's around 10 to the minus 7 or so. That's very good. Next slide. There's also no problem in the gravitational wave zone. This is also, of course, key because the payload from these simulations is the gravitational wave prediction, and the constraint violation is very low out there. Next slide. However, when we plot the constraint violation out near the outer boundary, the region of least physical interest to us, I have to point out, we see that 1, 2, 3, 4, count them, out of the 23 actually result in a code crash. There's an exponential blow up in numerical error that causes a code crash. And that is very unfortunate. Next slide. And it's caused by, and so I'm going to have to ask you to sort of flip through the next 3 slides back and forth. There you go. There we go. And go back. So what happens in black holes at home, just keep doing it while I talk. Thank you. What happens in black holes at home is when the grids move, the black holes move, the entire grid structure is interpolated to the new position of the grids. So you see the entire grid structure rotates. And that includes points near the outer boundary. Let's go to the next slide. There you go with the green circles, perfect. And what I found is sometimes these interpolations amplify numerical noise exponentially along that z-axis near the outer boundary. Next slide. And after a lot of experiments, I found that this instability is very sensitive to how frequently I regrid. In other words, how far do the black holes move before I decide to, okay, now it's time to perform the entire grid regridding. And it's very sensitive to that. I think that's a smoking gun, basically says, let's not regrid the outer, this large outer grid here, which is where we put our wave zone. This is not to scale, by the way. It actually goes all the way out to the outer boundary. Next slide. So my solution is very simple, and it is it's in a little movie. Just go through the next 4 slides back and forth. There you go. And so the solution is to simply there you go, to simply co-orbit, co-move the inner grids with the black holes as they orbit, and leave the outer one fixed. This seems to be, I think, a winning proposition for solving this problem. Next slide. But there are a couple of issues that remain, and they have to do with the fact that I need to look into my crystal ball. Black holes at home is not just going to be designed for binary black holes. I also want to be able to do binary neutron stars on this, magnetized binary neutron stars with these sorts of grid structures. And there's a real problem with that when it comes to GRMHD. We use the Illinois GRMHD code. It's a code I wrote and released open source. It's an Einstein Toolkit Thorn. But we've recently been developing a GRMHD library, a sort of numerical recipes for GRMHD. It's called the GRAIL library, GRHAYL. GitHub.com/that. You'll be transported directly to that code. And I actually want to do GRMHD with these grids. The problem is the way that we sample. So here's what we do. We put the space-time fields at cell centers. We put the GRMHD fields at cell centers, except for the magnetic fields. Now, for the magnetic fields, what we do is we actually evolve the vector potential. And the vector potential, if you put it at cell centers, you don't get a very well-behaved code. It fails certain GRMHD tests. And in fact, we found that it's equivalent to lowering your numerical resolution by almost a factor of 2. So we really don't want cell-centered vector potential if we can avoid it. Staggered is really the way to go. It's called staggered or edge-centered. The problem is if you sample at the edge, then you will on a spherical coordinate system, then what you will end up with is sampling right on the coordinate singularity. And sampling on the coordinate singularity is a vector quantity on a coordinate singularity. It's kind of like asking, okay, so let's say you're at the North Pole. That's a coordinate singularity in on our globe, and it's pictured here. Which direction is east, right? What is it? Vectors don't make sense at coordinate singularities. They're ill-defined. And in fact, that's one of the core ingredients to making numerical relativity and spherical coordinates work is rule number 1, never sample on the coordinate singularity. So it's very important that we avoid that. Bottom line is, this is having a z-axis at all, having coordinate singularities at all on our numerical grid structures is not a desirable thing for GRMHD, the way we want to do it. and the way I think should be done. I'm biased, of course. Next slide. Second problem is that, and I mentioned this before, there's an inefficiency in black holes at home. And it really happens, it's really worst at Q equals 1, mass ratio 1 to 1. Both black holes have equal masses. And the problem is, you see those blue dots there, the time step in numerical relativity simulations is proportional to the minimum distance between grid points. And for Q equals 1 all the way up to Q equals 4 to 1 mass ratio, the time step is governed not by the resolution near the black holes. In other words, not governed by the resolution as dictated by the physics, but is actually dictated by the fact that there's a coordinate singularity. There's a z-axis. There is that north pole, if you will, north and south poles on those spherical grid, those small spherical grids that are actually have tighter grid spacing, smaller grid spacing than near the black holes. That's bad. And that results in about an order of magnitude inefficiency for Q equals 1. Next slide. So to solve these problems, I propose to get rid of the z-axis. But how do we do that? Next slide. So let's start with a wholly spherical grid. Now, all those spherical grids you just saw, rewind one slide. All those spherical grids that you saw, rewind. Yeah, there we go. Are actually have holes in them. There's no r equals 0, so I actually avoid the worst of the grid focusing, focusing of grid points by just putting other grids inside these spherical grids. And in the innermost spherical grids, you see those are actually Cartesian AMR boxes. Next slide. Great. So we're going to start with one of these wholly spherical grids. It goes from little r from r in, which is greater than 0, to r out. This is the xz plane. Next slide. What we're going to do is we're also going to restrict theta in this new idea for a grid. We're going to set min theta to pi over 4 and max theta to 3 pi over 4. Next slide. We're going to call this the ring because it rules us all. And we're going to go from, and so let's now flip this grid. Next slide. The question is, how do we fill the gaps? How do we fill the gaps? So in the center, we're going to fill the gap with a Cartesian grid, just like we have in the past. And that seems to work extremely well. But how do we fill up this north and south pole region? Next slide. So let's flip the perspective. Now let's look at the XY plane. Now remember, this is a ring. We're going all the way around in phi, which is out of the plane of the screen. Next slide. Okay, now here's the XY plane. The ring, notice, is unbroken. It goes round and round. Phi covers from 0 to 2 pi, in other words. Next slide. What we're going to do is we're going to create a copy of that ring, and we're going to take 1/4 of it, exactly 1/4 of it. And you'll notice that if you pull this 1/4 slice out, you have a pyramid, a 4-sided pyramid with a rounded bottom and a rounded top. And this actually is a perfect, next slide, wedge. It's a wedge. And how do you fill in gaps over the poles? Well, you plug in these wedges. So next slide. We're going to rotate back to the XZ plane. And here is my proposed grid structure. I call it the wedge ring approach. The z-axis here, again, because it's the upper wedge and lower wedge are part of that ring, there's no axis of symmetry here. So there's no focusing of grid points up near the z-axis. Coordinate singularities no longer exist here. The wholly sphere has been replaced with 3 grids. Sphere is still smooth, both on the inner part, which, of course, because this comes from a radius, the inner radius of that ring, which is a constant r, and also the outer radius of the ring, which is a constant r. This is a smooth patch. So it's smooth on the inside, smooth on the outside, inner radius and outer radius. Next slide. All right, so I'm going to ask, if you don't mind, click on play. And so this is a visualization of what it actually looks like on the outer, play again, please, on the outer surface of this, this grid structure, this wedge ring approach. So the wedges look like little squares and they're patched over this ring, which is in blue. Thank you. Next slide. By the way, that visualization there was created completely in collaboration with ChatGPT. it's wonderful at doing matplotlib. Highly recommended if you haven't tried it. All right, and so again, this is the grid structure, Cartesian AMR in the middle, upper wedge, lower wedge, and ring. So that's to fill in this volume within this sphere, you need a total of 4 grids. Next slide. There's some great advantages over the original black holes at home. Like I said, there's no z-axis here in the spherical coordinate system. So there's no great grid focus. There's no north and south pole, if you will. So this increases the time step for Q equals 1 to by about a factor of 10. Smoother resolution, transition to Cartesian, actually, because there's no longer enormous grid focusing up there. Cartesian AMR is great. Cartesian grids are great in that they uniformly sample the points over a mesh. And also, I think this is going to be wonderful for GR-MHD. And I'll talk about a little bit more about that next slide. Next slide. But first, actually not, yes, the next slide, that's right. So we heard about cube spheres. Cube spheres is an outstanding approach for putting down grids. It's, I would argue, superior in many ways to just ordinary Cartesian AMR. And it has its own advantages over the wedge ring approach. Let me first talk about the advantages of wedge ring over cube spheres. First, there are 3 grids instead of 6. Second, if you want to evolve what is probably the most important, and I don't think Scott would dispute this much, probably the most important system that we need to model, those of us who do GR-MHD need to model, which is the black hole accretion disk. You can imagine here, right? So looking at the XZ plane, this is sort of the jet plane, if you will. So the jet goes up along the up and down directions. And then the disk plane there, the XY plane, the lower right, you notice that any fluid element in that disk never A, crosses any grid boundary, and B, it actually follows along coordinate lines. This is just a spherical grid after all in the XY plane. That's not true on a cube spheres grid, where you'll notice actually that in order to complete one orbit, that fluid element would need to actually cross 4 different grids. And also, I'll note that it doesn't follow along the coordinate lines, because on a cube spheres grid, there are actually these kinks at the grid boundaries. Finally, I'll say that Jacobians on the wedge ring grid, because they were based on ordinary or just a very slightly radially modified spherical grid, all of basically the reference metric, the spherical metric, right? If you look at it, it consists of some function of r times some function of theta times some function of phi at most complicated. In other words, I guess you could call it a separable coordinate system. As such, you only need to store f of r, g of theta, and h of phi independently. So if you want to calculate Jacobians derived from that spherical metric, all you have to do is store one-dimensional arrays. It's really, really cheap in terms of memory usage. And this is also the reason, unfortunately, why I can't use in black holes at home, because we're so memory constrained, right? We want to fit on a consumer-grade desktop or laptop. I can't use the cube spheres approach, which requires 27 grid functions, 3 dimensions, in all 3 dimensions to be stored for computational efficiency, so we don't have to recompute Jacobians and their derivatives over and over again at each time step. Next slide. That's not to say that wedge ring is the perfect grid structure, that it has its disadvantages. We already saw that in this previous movie. There's some grid overlap, right? There are wasted grid points. The good news is with black holes at home, the largest grid by far is the grid that goes to the outer boundary. And that grid takes up a large majority of it takes up the most memory usage of any other grid. And what we end up with is, despite the fact that we have grids overlapping, say we have cubes inside spheres, et cetera, the total waste is of order 10%. So you waste 10% of the grid points because, well, you have a corner of a grid cube within a spherical, within a spherical grid. But of course, with cube spheres, you can have much cleaner grid interfaces. So that that 3 dimensions of information basically enables you to set it up such that faces can touch faces with the same surface area. That's really nice. especially if you're thinking of this in terms of a finite volume GR-MHD approach. There's minimal grid overlap. You don't have to throw away hardly any grid points. Again, every grid point can matter. But that being said, you know, both have advantages, both have disadvantages. There's no perfect grid structure. Obviously, I have a slight preference because I'm biased, but toward wedge ring. But of course, I'm biased. So next slide. Great. So this is an actual grid structure that I propose. I'm not showing any of the overlaps between the grids just to make it easier on the eyes to interpret this. But this is a proposed wedge ring grid structure for binary black holes. You can see Cartesian grid there in the middle. You kind of see vertical and horizontal lines. You see the wedges, the rings. Now, remember I mentioned before that this Lego building block approach required that you set up the intergrid communications for every place where you have at least two grids that overlap. Here we have regions where there are 5 grids that overlap. This outermost region here, where you have a spherical grid, and inside that you have 2 wedge ring grids, there are 1, 2, 3, 4, 5 grids that overlap. Setting up the communication patterns between those such that information can propagate in a bidirectional way across any grid interface, that's really, really tough. It's tougher than anything I've ever tried before. So it's going to require a major advance in the way BlackHoles at Home does things. Next slide. And that major advance is what I call a universal multi-patch algorithm. So this is something I came up with in May of this year. And it took about a month and a half to fully implement. But the beautiful thing is now, it basically all you've got to do now is set up positions of grid and positions of your grids. Obviously, you want to set up the resolutions. And what you set up are the grid priorities, right? So let's say you have a Cartesian grid inside a spherical grid. Well, what gets the priority in terms of that boundary? Is it Cartesian grid, which has sharp corners, or is it the spherical grid that is, well, obviously more rounded? And that's what I mean by priorities. And the output is simply intergrid communication patterns. This will be, in my current plan is this will be the second BlackHoles at Home paper. I'll talk about the first one in just a minute, which is about to be released. This approach supports far more complicated grid structures. I have been successful. That grid that you just saw on the previous slide has been successfully, the communication patterns have been successfully set up. So I'm very excited about that. And what happened was in early June, so here's how my development works, right? So BlackHoles at Home is developed upon the NERPI infrastructure. I have to extend the NERPI infrastructure from time to time to get BlackHoles at Home to do what I need it to do. So what I do on an annual basis during each summer is I go and I take the advances I've made from my BlackHoles at Home fork of the NERPI infrastructure, and I backport them into NERPI. And I have to update occasionally some of the NERPI notebooks and whatnot to keep up with that. Well, I came to that this summer and I realized NERPI is sick. The poor baby seal. It needs to be rewritten. And this is not just my opinion, but most of my user base agrees. It was not designed to be as extensible as we've now made it, as we've extended it. It's not been designed for extensibility. Next slide. So I decided to rewrite NERPI, and I started on that early June. The core is nearly complete now. In case you're a NERPI user, please reach out to me, let me know, and I'll be happy to share with you our GitHub repo where we're doing this work. The bottom line is we're going to have a much easier user interface, easier onboarding for new users. It's going to be extensible. And you've heard from, and by the way, let me publicly apologize to Steve Grant for the fact that NERPI was not ever meant to be extensible, the original version. He's shown that NERPI can do amazing things if you really try hard, and he did. And it works great at generating automatically carpet and carpet X thorns using Steve's amazing extensions to NURPy. And one other cool thing is it'll be pip installable. So you just pip install and then start working. Extending it to new infrastructures, new numerical activity infrastructures, et cetera, will be, so you can automatically generate, for example, Dendro-GR modules or GR-Chambo modules, you name it, will be a possibility. Next slide. Finally, working on the first Black Holes at Home paper. I'm going to talk about that next, and that's going to be my final thing I'll talk about. Next slide. Next slide. Let's fast forward through these slides. We already know. Let's get to the movie. Next slide. Next slide. Great. We need to improve techniques, and that's what this paper is on. If you want to get numerical relativity working on a consumer grade desktop computer, normally, right, you choose either. Normally in numerical relativity, not thinking about desktop computers, you choose either increased accuracy at greatly increased computational cost. What I'm proposing here is there are techniques that we could try that would increase our accuracy without increasing our computational cost. That is what I'm going to talk about here. So the most popular approach in numerical relativity is the moving puncture approach, and it's built upon an excellent gauge choice, 1+ log lapse and gamma driving shift. And with this gauge choice, I don't know if anyone remembers the old infomercial, set it and forget it, but next slide. That's exactly what we're going for. You can see we don't need to excise the interiors of our black holes, which greatly simplifies the algorithms that we need to perform these evolutions for black hole binaries, binary neutron stars, et cetera. This approach has been implemented in Black Holes at Home. There are multiple moving puncture approach implementations within the Einstein Toolkit. I'm proud to be the creator of two of them, BiCall and BiCall vacuum. Next slide. But the problem with the moving puncture approach is that there's a sharp feature in the lapse. It's very prominent in binary black hole evolutions, and it's a result of the lapse. In fact, the gauge field, the lapse, finding a new equilibrium near the black holes. What happens is there's this sharp feature. It propagates out, hits refinement boundaries, generates constraint violation, generates numerical errors, in other words. And these reflections generate noise in the payload from our simulation, psi4, the gravitational waveform. It never goes away, and it causes inconsistent convergence. How much more do I need to describe? This is poison to a binary black hole evolution. Absolute poison. What do we do to address it? Next slide. Well, first, let me just show you what happens here. So the vertical line, the dashed lines here are Cartesian AMR grid boundaries, and this is the sharp feature in the lapse propagating out. I've rescaled the lapse so it's more or less constant, just so you can remove the radial dependence. And you can see that when it hits refinement boundaries, it reflects off of them. And you see that the noise never goes away, and you get reflections. This is just showing one dimension in a three-dimensional simulation. So there are reflections coming off of all over the place, refinement boundaries all over the place. Remember that the refinement boundaries are boundaries between resolutions, where resolutions, as you move from the strong field to the weak field, drop by factors of 2 discontinuously. So you have a sharp feature that propagates out. What do you expect is going to happen? It's going to hit a refinement boundary that eventually it cannot be resolved across, and it will partially or completely reflect. And we saw that in this movie right here. Next slide, please. There we go. So I published a paper in collaboration with the NASA Goddard group and Illinois group, and that back in 2014, that focused on 4 strategies for mitigating this problem. And what we found was applying all these approaches resulted in a Hamiltonian constraint violation of a factor of 20 lower, momentum constraint violation of a factor of 13 lower. The bottom line is what we're finding here, what I'm saying is a large majority of our numerical errors in these binary black hole evolutions in numerical relativity are caused by this wave, this sharp lapse feature, a large majority. By mitigating its impacts, by smoothing it out, et cetera, You can improve your convergence order, have less noise and errors in gravitational waveforms. The reason why I'd like to believe at least this has not been not currently in wide use, is because these original strategies were very, very difficult to implement, very dependent on the precise system that you're using, your grid structure, et cetera. Next slide. So that in mind, I've been working with BlackHoles at home to on my own approaches for improving and mitigating the effects of this sharp lapse feature. So this approach has been developed in BlackHoles at home. It is very easy to implement. That is the key here. So anyone should be able to benefit from this who uses the moving puncture approach. It's infrastructure agnostic, like I said. It's and I'll demonstrate in this upcoming paper efficacy of these improved techniques in the Einstein Toolkit with a modified version of Bicol vacuum involving binary black holes. Next slide. The first approach is what I call curvature-aware Kreis-Oliger dissipation. The idea is you reduce the strength of the Kreis-Oliger operator, the strength of the Kreis-Oliger operator near the black holes. You just basically multiply the Kreis-Oliger strength by, I believe it's psi to the -2. So it basically drops the strength of Kreis-Oliger to 0 near the punctures, and you can increase the Kreis-Oliger strength parameter to 0.99 on the lapse only, and that will greatly reduce the noise generated by the lapse, that sharp lapse feature. Next slide. Curvature-aware Hamiltonian constraint damping. This is a modification to the BSS formal factor evolution equation. And again, this is actually a parabolic term, so it's another low-pass filter, just like Kreis-Oliger. And the idea again is you don't want to apply low-pass filters to regions where you have really strong space-time fields, really sharp space-time fields, where you actually like to have the space-time fields be sharp. And the idea is if you lower its strength, again, by some power of the conformal factor, lower its strength near the black holes and increase its strength farther away. You can increase its strength farther away and actually have a very effective means to dissipate any constraint violation generated by this outgoing lapse feature. This is not something applicable to Z4C or CCZ4, but it is very applicable to vanilla BSSN. Next slide. Combined results, very cool. A factor of 100 less Hamiltonian constraint violation, factor of 10 less momentum constraint violation. There's another technique I'll be reviewing in the paper that decreases these constraint violations by more orders of magnitude. Stay tuned for that. Paper will be coming out soon. Thanks so much. That's all I have to say. Any questions if we have time?
Can you hear us, Zach?
I can hear you now. Yeah.
Any questions? I encourage you to come up here to speak, please. Carlos, while Vasily comes up. Carlos, do you want to say your?
So Zach, nice talk.
Thank you.
I really, it's very important to improve gauges. That's a practical way of improving accuracy. Your qualification of deviations of the lapse from one asymptotically or during evolution as poison, I think it made me remember when in movies a guy goes to a bar and the barman asks him what's your poison, and you say whiskey or so on. So we can drink this and have fun and enjoy for many years still without killing us. And the point I want to make actually is we have recently been able to evolve black holes with mass ratios 1,000 to 1 with very low level of radiation, and have been able to capture the emission of these gravitational waves with within an error of 1 part in 10 to the 8 with these traditional gauges. So indeed, there are circumstances where you can improve the gauge, but it's not killing us, not anytime soon.
Oh, that's great to know, and I'd love to see the secrets behind that success. Also, I'd love to see the high mass ratio. Sorry, the high for high mass ratios, the high L and M modes. Those are very important, of course, to get right for these high mass ratio systems. But wow, kudos! That's very impressive.
Vasily?
Right. Hey, Zach, nice talk. A technical and a philosophical question. In
Yes.
that drop-off of the L equals 8 mode, did you extract that in spheroidal harmonics? Because otherwise you should see some ringing from the mode mixing, right?
Yes, but that is a minor effect as compared to the noise in most evolutions. But yeah, no, it was in spherical harmonics, ordinary spherical harmonics. And I'll say that I have compared L equals M equals 8, the amplitude of that mode versus the only other numerical activity code whose catalog contains L equals M equals 8, and that is the spec catalog. And I'm excited to report that my level of noise is less than specs even. And I mean, it's obvious to see the impacts of noise. It's sort of a high frequency feature. It doesn't look anything like a mode mixing.
Okay. And then the philosophical question. So the grids become ever increasingly complicated and more patches and all that. At this stage, would it be easier to start from scratch and use unstructured grids or something like that, or equiareal grids and just do finite elements?
That's a good question. Again, the point of black holes at home is to fit onto a consumer grade desktop computer. And what I found is if you want to just start with a bunch of deformed Cartesian cubes, you actually have to store the Jacobians in memory as well as all the space-time fields, et cetera. And I'm not convinced. I mean, look, I'm doing this at 8th order finite differencing. I'm not convinced it'll still fit into memory. If I started from scratch again today, I'd probably do the same. I'd try the same approach, just because. I mean, yes, it may look like the grid structure are somewhat more complicated, but in reality, we're going to have to break up our grids anyway when we parallelize black holes at home, which is in the works. And hopefully we'll have a big update on that next year. As I'm hiring a postdoc to work on that full time, starting in August. And yeah, so stay tuned for that. More grids may not necessarily be a bad thing. Like I said, at the end of the day, you want to break up your grid structure anyway. So thanks.
Thank you.
Any other questions?